Thank you. So I changed the title slightly to make it more targeted at economists rather than social science in general, because I realized most of the content of my talk was actually going to be more focused at economists. So this talk is going to be about a course for first-year graduate students that I developed to distract myself from the slow progress I was making on my PhD research during my PhD at the University of Edinburgh. So just to get started, I should probably thank the Scottish Graduate Program in Economics who partially funded my trip to give this talk here today, as well as the Scottish Institute for Research in Economics who contributed the other bit of the funding. And then my current affiliation, I'm a postdoctoral research fellow with the Institute for New Economic Thinking at Oxford University, and I'm also a postdoctoral fellow at the Oxford Mathematical Institute. Okay, so here are my research interests. This is probably going to be nothing to any of you unless you have an economics background. What I'm really interested in is multi-agent systems modeling and agent-based modeling. I would like to learn how to build multi-agent systems models of economic systems. So if you know anything about that, please come and help me, because that's what I'm interested in terms of research. So just to give you an idea of a motivating use case that I use in the classroom for, sorry. Oh, there we go. First use of the IPython reveal slideshow. So just a little bit, kind of a quick plug for Scotland. If you've never been to Scotland, you should go. It's an amazing country. My son and I are hiking in Glencoe. A bit more about my background. I have a PhD in economics, an MSc in economics, and applied maths I did as an undergraduate. It seems like such a long time ago. I also spent some time in the private sector. This is a bit unusual for an economics PhD. Usually economics PhDs go straight from undergrad into grad school and into a PhD program, and despite the fact that they study economics, they've never had a job outside of academia. Research interest. Okay, here we go. So, motivating the use of numerical methods in economics. So I start out by trying to provide a simple motivating example. And the motivating example that I use to most of my students is the Solow model of economic growth. So this is a model that it's a very, very simple model of economic growth as a process of capital accumulation. And it also has two other sources of growth, population growth and technological progress. Now, the basic prediction of this model is that long-run growth in per capita income is driven by technological progress and not by capital accumulation. So the model doesn't so much explain growth as it does assume it, because the technological progress will be completely exogenous to the model. The point of using this model as a motivating case is that all of my students will have seen this model probably 4 times at least during an undergraduate training in economics. They'll have seen it in their first and second year because it's several chapters of the leading undergraduate textbook are devoted to this model, and they will have seen it if they have taken kind of a previous graduate training in economics, because the first several chapters of the most commonly used textbook at the graduate level are also devoted to this model or some derivatives of it. Okay, so here's the model. It's a single nonlinear differential equation with an initial condition. Now, the way that this is taught, the way that it's taught in the classroom at the undergraduate and at the graduate level is to make sufficient assumptions about this function f, which is basically the production function for the economy, such that you can solve this model analytically with pen and paper. Typical assumption is to assume that the function f has that form. And if you assume that the function has this form, then the model makes a specific prediction about factor shares, which is basically the way that the output or the income of an economy is divided between the factors of production. And in this model, that's basically labor or capital. And it makes a specific prediction that the fraction of output or income that is going to be going to workers in the economy is a constant. Now, unfortunately, that prediction is pretty much falsified by the data. If you go and you look at the data for factor shares in most countries, you will see that they're declining. And so the way that this model is taught in most graduate programs and most undergraduate programs, with the assumptions that they make in order to maintain analytic tractability so you can avoid using numerical methods, and requires making assumptions that are just fundamentally contradicted by the data. And this has been a very effective use case for me in motivating why students should care about numerical methods when they come from a background where they haven't been exposed to them, and they come out of undergraduate thinking that, oh, all of the analytical techniques that I've been taught and all the maths that I've learned is completely sufficient for me to understand the economic world. And you can make some simple extensions of this baseline model that will be able to capture the property that you see in the data, the variable factor shares that I was talking about. But as soon as you make this relatively simple extension of the underlying model, you break the analytic tractability. You can no longer solve the model with pen and paper. And so students, when confronted with this, most economics students coming out of undergraduate standard undergraduate training will not know what to do at this point. They will not know how to go about solving this model with a simple extension that allows you to capture a key feature of the data. Now, in order to solve this model, you would have to use some not terribly sophisticated numerical methods. You need to be able to integrate a single nonlinear differential equation. You might want to do a bit of looping over parameter values in order to see how that solution is going to change. Or you might want to do something slightly more sophisticated by trying to estimate the model parameters from the data using maximum likelihood or nonlinear least squares or Bayesian methods or things like this. Okay, so what other kinds of methods are economists using? So I would say pretty much the same methods that are going to be used in any other hard science. So we're going to use linear equations and iterative methods, 1D multidimensional optimization, linear and nonlinear optimization, nonlinear equations, approximation methods. Economics has a lot of functional equations that need to be solved. This is just to kind of give you guys in the audience a sense of what economists who use numerical methods are actually using. And this basically is just the first 6 chapters of Numerical Methods for Economists by Ken Judd, which is kind of the only textbook that tries to take the applied maths literature and focus it in a way that economists can try to consume it. Okay, so a bit of background about numerical methods. So here's my course. So some quick demographics. So I teach a relatively large class size, it seems, just relative to some of the other class sizes that were mentioned in talks yesterday. So I have about 60 to 80 students in class. So the median student is a Windows PC user, and we have we have students in the UK who come from all over the world to study. So not only are they going to be running a Windows PC, but they're going to have different flavors of Windows. Some will be very old. Some of them are going to have, because they come from countries where the native language doesn't work well in ASCII, they'll end up having non-ASCII characters in their file path names, which causes all kinds of installation problems for lots of software. They're primarily going to be using computers to browse the web and send email, maybe do a little bit of LaTeX, but they're not really using their computer to crunch numbers in any way. Yeah, okay, yes, thank you. Facebook. They will have had 1 or 2 semesters of stats or econometrics training, and they will probably have used Stata or SPSS, possibly R, but they will not be terribly familiar with even a basic scripting language. So the way I teach the course is it comes basically in 2 components. The first component is a set of lab sessions. There are 8 3-hour Python-based lab sessions and they're designed to run concurrently with their core macro sequence. So they go into the lecture theater, they spend, I think about 3 to 6 hours with each component of the core macro sequence, being taught about a specific model or a specific class of models. And then what I try to do in the labs is basically show them the types of numerical methods that they would need to solve the models that they have learned in class. So I try to supplement what they've already been taught. So in that way, what I choose to teach them has been slightly constrained. Okay, so the material for the 2 introductory labs, which basically I get 6 hours to kind of teach them roughly what Python is, how you might program in Python, and what you can do in terms of scientific computing. And I make heavy use of a book on quantitative economics that is written by Thomas Sargent and John Stokowski and is available online. This is just to give you, there it is, an idea of the type of stuff that I cover very quickly in the first lecture. I get them set up using the InThoughts Canopy Python installation in the lab, and we just kind of go through some introductory examples and some Python essentials. I try to get them coding as much as possible. So I don't talk very much. I show them the code and the exercises, and I just say, just kind of work through it and ask questions as much as possible. Okay, so the material for the 6 remaining labs, again, is designed to complement the core macro sequence on the Scottish graduate program. And so it varies a little bit from year to year. So this past year, I covered finite difference methods for solving initial value problems, which is the simplest type of methods that you could use to solve the solo growth model. Finite difference methods for solving boundary value problems. The next kind of extension of a solo growth model is to drop some dynamic optimization into the model, and that changes the model from a single equation with an initial value to a system of 2 differential equations with some boundary conditions. We do numerical dynamic programming. And then dynamic stochastic general equilibrium modeling. And just to give you a flavor of the notebook that I use, one of the notebooks that I used in class. So this is the notebook that I use to teach dynamic stochastic general equilibrium modeling. And I tend to try to break the lab notebooks down into 2 components. The lab sessions into 2 components. The first 2/3 of the labs are really devoted at trying to deepen the students' understanding of the model that they're taught in the lectures using lots of graphs. So what can you do? So what does your utility function look like? Most students have been using utility functions from the first day of the first term in undergraduate. Many of them will have never bothered to actually plot a utility function to see what it looks like. So we spend a lot of time plotting, in this case, utility surfaces, and then doing a bit of comparative statics on the various utility functions, trying to get them to build some intuition for what it means to vary the parameters of the utility function. Look at key trade-offs between choice variables in the model. In this particular model, a household has to choose consumption and labor supply. And so there's this trade-off that the agent has to make between what is the optimal choice of consumption versus labor supply. And we talk about that and try to build their intuition about that. And then in the last 2/3 of the lab, or sorry, the last third of the lab, rather. The last third of the lab is devoted towards doing more sophisticated, let me get down to it here. Oop, too far. So the last third of the lab is devoted towards actually solving a full model. And in this case, I make use of a C++ program called Dynar++. It's a stripped-down version of a MATLAB-based program that is the dominant toolkit for solving this class of models within economics. And I show them how to use it, and I explain a little bit about the methods behind it. And but again, a lot of it is showing them how to use the tool to generate plots and giving them a flavor of what the methods are doing, with the idea that some subset of these students are really going to get into the methods and then will use them over the summer in an environment where I can teach them a bit more about the course. Okay. So one of the things that has been fairly successful in the first 2 years of my teaching this course is to try to get students involved in extending the course materials. So last year, and then again this summer, I have a couple of MSc students that I'm supervising to basically write their own IPython notebook labs that are based around their MSc dissertations. So I kind of help lead them along in taking a lab sheet that I've already written and effectively modifying it to the model that they're looking at. So they can start from having a lab sheet where they just go through the first 2/3 of it is learning about the model, and so now they're learning about the model that they're actually working on for their MSc thesis, or MSc dissertation, and then the last bit of it is basically using the same tools that we used in the lab to solve their model. Right. Okay. So the second part, thank you. The second part of the course is the Python Bootcamp. And so the Python Bootcamp, basically what I tell students at the beginning of the year when we start into the labs, I say, what I'm going to do in these labs is I'm going to give you an idea of the possibilities of what you can do with these tools. I'm not going to teach you to program. I'm not going to teach you the deep theory behind these methods. I'm just going to try to show you what's possible and get you excited about learning more. And then I tell them, if you're interested in learning more, the first week in June of every year, I commit to spend 40+ hours of my time over the course of a week teaching you how to program in Python. And then some students will select into coming and attending that boot camp. Now, the way that I run the boot camp is I split it into 2 sessions. We have morning sessions and afternoon sessions. The morning sessions follow the excellent Think Python book by Alan Downey, and I divide it up into chunks so we can try to cover at a very fast pace the entire book in a week. And this year we had some students almost get all the way through the book in a week and seem to more or less understand, not at a deep level, but at each point in time they felt like they understood what was going on, which is really kind of exciting. During the afternoon sessions, on the first day is a lot of software install. I kind of very quickly install the Canopy distribution, Git, explain a bit about version control, walk them through how to use the IPython notebook, and then on the afternoon sessions of the remaining days, I basically show them the possibilities in quite a lot more detail of NumPy, Matplotlib, and SciPy, kind of the founding open source libraries for scientific computing. So this is the second year I've run the boot camp. The first year I didn't advertise outside of our SGPE, and we had a small group, about 12 students, who attended the course. So this year we did advertise, but only outside of the SGPE via the Scottish Institute for Research and Economics, which basically just broadcast the fact that I was going to teach this course the first week in June to other researchers throughout Scotland. And we had 50 students registered interest within the first 2 days of advertisement. And then I had to shut it down because I was really worried about teaching more than 50 students basically by myself with the help of one TA. But we had undergraduate students from economics. We had the MSc students, the PhD students from 5 Scottish universities, PhD students from 2 English universities. I'm not actually sure how the English students found out about the course because it wasn't really advertised outside of Scotland. And then I had a faculty member who came from Birmingham to take the course. So I really felt like this was an indication that there's quite a lot of demand for scientific computing training amongst economists in the UK. So I'm basically done. So where to go from here? So first, I need to incorporate all the great ideas that from yesterday and that I'm sure I'll pick up over the rest of today and tomorrow. A lot of things like widgets and all kinds of ways to make the notebooks more interactive. I need to do that. I'm not doing enough to teach reproducibility. So it's hard in the lab sessions to do that because using Git requires a bit more technical sophistication and understanding than just using Python. But still, even in the Python Bootcamp, I'm not doing enough to preach reproducibility. And my course is a good entry point, but I'm not teaching enough state-of-the-art methods and using state-of-the-art solvers and algorithms for the PhD students who would want to use it in their own research. And that's it. Thanks.